Curvilinear coordinate systems 21. A static magnetic field is related to the current density by one of Maxwell's equations. Curl B is equal to mu 0 J. In part A, we have the magnetic field given in terms of the cylindrical coordinates for rho less than rho 0 inside the cylinder, and we calculated the current density. Now in part B, if B is equal to 0 for rho greater than rho 0, how much current must be flowing in a cylindrical shell at rho is equal to rho 0? Now given that, we know that this is the current density for rho less than rho 0. Now, if this is the current density that's flowing in z-hat direction, so this is our z-axis here, now I can see that I need a current in the opposite direction in order to cancel out the magnetic field, so that I would have zero magnetic field outside. And the magnetic field was in phi hat direction, which is the tangential axis on the xy plane. And if I use Ampere's law, Ampere's law states that the closed contour integral B dot product with ds is equal to mu 0 current enclosed, which is an application of Stokes theorem. And we're going to use this for rho greater than rho 0, where the current enclosed has to be equal to 0, so that the magnetic field outside has to be 0. So we conclude that an equal and opposite current must flow at rho is equal to rho 0 shell. So we need to have this condition satisfied. And how do we calculate the total current inside? It's the current density J dot product with the area vector dA. And now we have the current density given here. The area vector is going to be for a cylindrical shell, we have a small differential area dA that is given by dA is equal to rho d phi multiplied with d rho. So if you look at this, this is rho d phi, and here I have d rho. So this part is d rho, this part is rho d phi. So we have this differential area. And that area vector is going to be, by following the current direction, I can see that that area vector is going to be perpendicular to this area. So I have the dot product now if I write the area vector dA as rho d phi, and the current must be flowing perpendicular to this area, so that I'm going to have the area vector defined by this shell is going to be in minus EZ hat direction. Because the current has to flow in the opposite direction. So following the direction of the current, this is going to be in minus EZ hat direction. So the current density 4B0 divided by mu 0 rho 0 cube double integral rho square rho d rho d phi. This will give us because the area vector is in negative direction, this will be with a minus sign. This is EZ hat, and there the area vector is negative. So I'm going to get, for the total current that flows on this shell, to be 4B0 divided by mu 0 rho 0 cube. I have a phi integral, for phi goes between 0 and 2 pi d phi, and I have the rho integral, which is integral 0 to rho 0 rho cube d rho. So here I have rho square, but here I have rho d rho, so it's going to be rho cube. And let's do this for the current that's flowing inside, so that the area vector would be in EZ hat direction, not along the shell. Okay, so this is, if it's inside, then I would have an area vector in plus EZ hat direction. And this integral will give me it's a fairly simple integral. 4B0 divided by mu 0 rho 0 cube. From the d phi integral from 0 to 2 pi, I'm going to get 2 pi. And as rho varies between 0 and rho 0, I will have rho 0 to the 4th power divided by 4. So I can see that these 4's will cancel, and this rho 0 cube will leave a single rho 0 up front. So this will give me, for the current inside, 2 pi B0 rho 0 divided by mu 0. That's the total current that flows inside. So I conclude that for rho less than rho 0, I have the total current, it's a uniform current, the total current, 2 pi B0 rho 0 divided by mu 0 in EZ hat direction. So this is the total current that flows in EZ hat direction. So I have taken the area vector inside for this differential area to be in plus EZ hat direction. For the current that flows outside, I must have total enclosed current to be equal to 0. Then I need at the shell, rho is equal to rho 0, a current which is in the opposite direction, and it's equal to minus 2 pi B0 rho 0 over mu 0 EZ hat. The total current must be in minus EZ hat direction, so that when I look at the total current enclosed by this loop, it's going to be, this total current is being balanced by this total current that flows in the shell in the opposite direction, so that I will have zero magnetic field inside. From this equation, current enclosed will be zero. All right, so for this problem, we know the magnetic field inside is given by this expression and outside is zero. And we can use Maxwell's equation, curl B is equal to mu 0 J. If we do the integral curl B dot d sigma, we would get the closed contour integral B dot ds, and that's equal to mu 0 times current enclosed. That's an application of Stokes theorem. And this tells us that if you want to have a magnetic field outside to be zero, the current enclosed by this loop has to be equal to zero. So if the J is flowing in EZ hat direction, we have a non-uniform current that varies with rho. We must have an equal and opposite current that flows in the shell to cancel out that current. So in order to calculate the total current that flows inside the sphere, I do integral J dot dA, where the area vector is defined by the current direction. So this is in plus EZ hat direction. And for a differential area here, I'm going to have rho d phi d rho, as we can see from this sketch. And when I do this integration, dot product with EZ hat rho d phi, I obtain 2 pi b0 over rho 0 over mu 0 as the total current that flows inside the cylinder. Now I need to have an equal and opposite current minus 2 pi b0 over rho 0, mu 0 rho 0 over mu 0 in minus EZ hat direction. So that I get enclosed current to be zero.